Chemistry, we're on to next lesson in the acid bases unit, and this is on the subject of buffers. So what is a buffer? A buffer is a conjugate acid-base pair designed to resist changes in pH if small amounts of acid or base are introduced to the solution. So human blood, for example, contains a buffer carbonic acid and its conjugate base, the bicarbonate anion, in order to maintain a blood pH between 7.35 and 7.45. A blood pH value higher than 7.8 or lower than 6.8 can cause death. So buffers are created from a conjugate weak acid that will neutralize hydroxide OH- ions and a conjugate weak base that will neutralize hydronium H+ ions. Neutralized H+ and OH become neutral water molecules. Buffers must be created from a conjugate weak acid-base pair. A random acid-base pair will react with each other in unpredictable ways and cannot act as a buffer. So acetic acid CH3COOH and the acetate ion can act as a buffer because they are conjugates. But acetic acid and a fluoride ion cannot act as a buffer because they are not conjugates. Again, a conjugate acid and base differ from each other by exactly one proton. So acetic acid and the acetate ion are a conjugate acid-base pair. The acetic acid CH3COOH buffer defenders will guard against strong base invaders. So they're the strong base invaders. They were produced when 3-sodium hydroxide dissociated. The OH- hydroxide invaders will want to raise the pH of the solution. These are the acetic acid defenders of the solution. They want to protect the solution from pH change. So when a defender fights an invader, both will neutralize and no longer exist. As long as there are more defenders than invaders, the solution will be protected and the pH will almost not change. So we learned in an earlier unit that a weak acid, when in the presence of a hydroxide ion, will 100% of the time donate its proton to the hydroxide. It will only occasionally donate a proton to a water molecule, but it will always donate it to a hydroxide. So there we see one of the weak acid defenders has a cannonball. That's the proton that it's going to donate. So it fires it at the invader. And what happens to the invader? That's a hydroxide plus a proton becomes a water molecule. So it's neutralized. That doesn't change the pH of the solution. Now, what happens to the defender that just fired the cannonball? That was an acetic acid minus the proton, so it becomes an acetate ion in the solution. Now here comes another invader. Another cannonball from a defender. There it goes. Turns that hydroxide into a water molecule. Perfectly harmless, perfectly neutral, won't change the pH. The defender, though, becomes an acetate ion and goes into solution. Now there's one more invader. Cannonball gets fired at that invader, becomes a water molecule, and another acetate ion goes into the solution. So there are no invaders left, but there are two defenders. The pH remains almost unchanged. The acetate ions in solution slightly raise the pH, but not nearly as much as the hydroxide invaders would have. So let's examine that. So let's say you had 10,000 hydroxides coming into the solution. That's going to greatly change the pH and drive it up towards 14. Let's say, though, you had 10,000 defenders to neutralize those hydroxides. Then those 10,000 hydroxides would turn into water molecules, and the 10,000 acetate ions would go in the solution. But acetate ions are a base. Isn't that what we wanted to not happen to the solution, is for it to become more basic? But remember, the acetate ions are only a weak base. So let's just say that those 10,000 acetate ions, only one of them is going to do what a weak base does, and that is draw a proton away from a water molecule and turn that water molecule into a hydroxide. So, in other words, instead of having 10,000 hydroxides going into the solution, you only have one, the one that was created by the weak base. So that's a good trade-off. It's better to have one hydroxide than 10,000. And so that's what happens. So the acetate ions will produce some hydroxides and will slightly raise the pH of the solution, but not nearly as much as it would have happened if those 10,000 hydroxides from the strong base had been able to enter the solution. Now the solution also has acetate ions. Before the ones that you see were formed, it already had acetate ions to defend against a strong acid, but they aren't needed in this particular reaction. We'll see them in the next reaction. Okay, so these are hydronium ion invaders from a strong acid, hydrochloric acid. They want to lower the pH of the solution into the acid range. These are the acetate ion defenders of the solution. They want to protect the solution from pH change. So what those strong acid molecules are going to do is fire a proton into the solution. They want to hit a water molecule and turn it into a hydronium ion, which is exactly what you don't want to happen. But what the weak base defenders will do is intercept that proton every time and prevent it from going to a water molecule. So let's see that happen. So the acetate ion buffer conjugate base defenders neutralize the H+ strong acid invaders by accepting a proton until one of the two runs out. So there's a proton that's going to come from that hydrochloric acid. It goes up, it hits that defender. The defender then becomes an acetic acid molecule and goes into the solution. The chloride ion, the hydrochloric acid rather, turns into a chloride ion. Now a chloride ion, while it's electrically an anion, negatively charged anion, from an acid-base standpoint it's neutral. It's neither an acid nor a base. It has no protons to give off. It won't accept back a proton, so it just sits in the solution as a neutral chloride ion. Now here's the second invader, fires it. Acetic acid goes into the solution and you have another chloride ion which has no effect on the pH of the solution. Third one fires, there goes another acetic acid into the solution and another chloride ion. Of course the chloride ions, everything that's happening here is happening down in the solution, but for our metaphor we're showing it happening up above the beaker. There's a fourth one, same thing happens, an acetic acid, and finally there's a fifth one. So now you have 3 hydrochloric acid molecules and no defenders left. And they want to lower the pH. So what's going to happen now? When a defender fights an invader, both will neutralize and no longer exist. This time there are more invaders than defenders, so the invaders win and change the pH of the solution. And this happens like this. With all the buffer defenders gone, the remaining HCl strong acid invaders are free to pass protons to water molecules and create hydronium ions. This will lower the pH down into the acid range. The buffer has been defeated. And there they go. So now you have hydronium ions, which are the characteristic of an acid. pH will hold only as long as there are more buffer defenders than invader strong acid or strong base. Okay, now we're going to talk about the subject of salts. So to create a buffer, you must understand what a salt is. When an HF, hydrofluoric acid, weak acid molecule dissociates, it produces its conjugate base, the fluoride ion, F-. This is a reversible reaction, so the F- base can take back the same proton or a different one. So the conjugate base of a weak acid will be able to take back a proton, unlike the conjugate base of a strong acid, which never takes back a proton. So the fluoride ion F- is the conjugate base of hydrofluoric acid. A salt is a neutralized acid or base. Neutralized means that it is neither an acid nor a base. So there you have a weak acid, and it gives off a proton. So a salt is formed when a 1 plus cation such as sodium, in other words something else with a positive 1 plus charge other than a proton, attaches to the conjugate base or some other weak base. So there that fluoride ion lost, the hydrofluoric acid lost its proton. Now it's a fluoride ion, F-. So a positively charged Na+, remember sodium takes on a 1 plus charge, that's going to take the place of the proton. So the Na+ and the F- form an electrically neutral ionic bond. This bond will only form out of water, but will dissolve 100% in water. So the fluoride ion F- and any cation such as an Na+ form a basic salt. It's formed from the conjugate base, so it's formed from a base, but it's a neutralized base because that Na+ is not going to act like an acid the way a proton would. The hydronium ion is then moved off to the side. Okay, so we'll see the role that has in creating buffers. NaF is called a basic salt because it is formed from the neutralization of a base, in this case F-, the fluoride ion. An acidic salt is formed when a weak acid is neutralized by an anion, such as the chloride ion. So here we have an ammonia, NH3 molecule, that is a weak base and can accept a H+ proton from a water molecule. So again, it's a weak base, so it will only occasionally will this happen, but it will, and it will produce an NH4+. So that's the conjugate acid of ammonia. And when it does that, it produces a hydroxide ion. That's the definition of a base. Base produce OH- ions in solution. An acidic salt is formed when a weak acid is neutralized by an anion such as the chloride ion. So the ammonium ion, NH4, has a 1 plus charge because it accepted that proton. The halogen group, fluorine, chlorine, bromine, iodine, form 1 minus anion. So go ahead and see your charge number by ions sheet. Chloride takes 1 electron to form a 1 minus ion. So there they join together, the positive charge of the ammonium and the negative charge of the chloride ion. An acidic salt is formed when a weak acid is neutralized by an anion. The ammonium ion NH4 has a 1 plus charge. NH4 plus creates an ionic bond with chloride to form ammonium chloride. This molecule is called ammonium chloride. It is a neutralized NH4 plus acid molecule. A neutralized acid molecule is called an acidic salt. So let's review the relationship between weak acids and hydroxides, and between weak bases and hydronium ions. So hydroxide OH- has such a strong pull on protons that it will cause 100% of weak acid molecules to dissociate. Remember, weak acid in the presence of only water will only occasionally pass a proton to a water molecule. But in the presence of hydroxide, it will pass 100% of the time. It will pass its proton over. So this means that every strong or weak acid molecule that enters water will give a proton to a hydroxide molecule. So there you see that happen. And what happens to the hydroxide? It turns into a water molecule, which is neutral. This is important because every strong base molecule, OH- that enters a solution can be neutralized by a weak acid so that the pH of the solution does not change. Now let's look at the other situation. Here we have 4 weak base molecules, the fluoride ions, and 5 strong acids, the hydrochloric acid molecules. So they all enter the solution. So a strong acid, HCl, is placed in aqueous solution of a weak base, F-, the conjugate base of hydrofluoric acid. Will the protons donate to the water molecules or to the fluoride ions? The strong acid H+ protons will first dissociate to the weak base fluoride ions, as you just saw. Only after all the fluoride ions have been consumed does the HCl dissociate to the water to create H3O+. So what that means is that if you have enough weak base ions, you can protect the water molecules from becoming H3O+, because the fluoride ions will be the first ones to attract the hydronium ions, or the protons, and then only after they've been used up, after the fluoride ions have been completely consumed, then will hydrochloric acid pass a proton to a water molecule. So to create a buffer, we need to choose the pH you want to hold stable, choose a conjugate weak acid-base pair with an acid pKa equal to the desired pH. We're going to talk about that in a later lesson. Use an equal number of moles of weak acid and its conjugate base salt so that you protect equally against strong bases coming into the solution and strong acids coming into the solution. Or use an equal number of moles of a weak base and its conjugate acid salt. So you can create a buffer out of either a weak acid and its conjugate base or a weak base and its conjugate acid. Determine the number of moles based on the quantity of acid or base to be neutralized. So we will use a weak acid, hydrofluoric acid, and its conjugate base for this example. So there you see 5 hydrofluoric acid molecules. And let's just say, for the sake of keeping the numbers simple, we're going to say that 1 out of 4 of those hydrofluoric acids dissociates to water. So first we need to produce an equal number of moles of hydrofluoric acid in the fluoride ion so we can guard against equal numbers of strong acid and strong base molecules. So we will use simple numbers to say that 1 out of 5 hydrofluoric acid molecules will dissociate to produce a fluoride ion. So now you have 4 hydrofluoric acids and 1 fluoride ion. This would represent the equilibrium concentration of hydrofluoric acid and fluoride, 4 HF for every 1 fluoride ion. The equilibrium concentrations of hydrofluoric acid and fluoride will serve as a buffer. HF, hydrofluoric acid, a weak acid, will guard against 4 molecules of invader strong base. But there's only 1 fluoride ion, so that will guard against 1 molecule of invader strong acid. 4 times as many strong base molecules can be neutralized as strong acid. We would like these numbers to be equal. We'd like to guard equally against either strong base or strong acid. The problem is, if we add more hydrofluoric acid molecules, we will produce more fluoride ions. However, the ratio of hydrofluoric acid to fluoride will continue to be 4 hydrofluoric to 1 fluoride. So there you have 4 to 1, but if you keep adding hydrofluoric acids, every 5 hydrofluoric acids, you're going to end up with only 1 more fluoride. So you continue to get this 4 to 1 ratio, and that's not what you want. You want them to be equal. So how do we solve that problem? So how do we add F- ions without adding more hydrofluoric acid molecules? The answer is to use the conjugate base salt for hydrofluoric acid, or a conjugate base salt, and one example would be sodium fluoride. We will add 5 NaF, sodium fluoride, base salt molecules to the solution. So there's 1, 2, 3, 4, and 5. So what happens to those when they go into the water? This sodium will immediately dissociate. From your solubility rules, the sodium plus ions completely dissociate from the fluoride ions. So now you have about roughly equal hydrofluoric acid molecules and fluoride ions. We can now see that the sodium fluoride and hydrofluoric acid both produce a common ion, F-, fluoride ion. From our earlier common ion problems, and according to the Chatelier's principle, the concentration of F- ions is greater than equilibrium. This will push the reaction back toward the reactant side, which is hydrofluoric acid. The excess fluoride ions above the normal equilibrium concentration will push the reaction back to the left to create more hydrofluoric acid molecules. So you can see that reaction down on the bottom. And there it goes. and it's going to draw a proton away from a water molecule, and so now you have equal numbers. So we've accomplished our goal. We have the same number of hydrofluoric acid and fluoride ions to neutralize the strong acid invaders. This is how to create a buffer starting with a weak acid. A buffer is created by using a weak acid and a salt of its conjugate base. The buffer can now guard against hydroxide and hydronium invaders equally. A buffer from a weak base can be created in the same fashion. So just remember this concept to create a buffer. A buffer is created by using a weak acid and a salt of its conjugate base. And that concludes this introductory lesson on buffers.